Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides on this during this trip to ESO's Paranal Observatory. So, just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010. I have also worked for the Astronomy Center of the University of Antofagasta, and regarding my personal hobbies, I am interested in astrophotography. But as I told you already, I am not alone. I am with Hector, and Hector will be the producer today. How are you, Hector?
Hello, Farid. Hi, I'm happy to be here once again. So I'm Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, in Germany. I work mostly with topics related with the circumgalactic medium, that is the environment that surrounds galaxies. And I have been a member of the team of guides for Paranal Observatory since 2019. I started while I was doing my master's in the University of Antofagasta. And as Farid mentioned, today I'm going to be the producer, and this means that I'm going to be changing the pictures, the videos, but I'm also going to be reading all your comments. So please send all your questions, all your comments, your greetings, and if you have any doubts, there will be a couple of times during the tour for answer them. Okay.
Okay, thank you very much, Hector. So yeah, in this case, ESO wants to be with you during this virtual visit, Sunbeam Astronomy, directly to your home or wherever you are. So please remember to send your questions or comments during all this streaming. So in some portions of this virtual experience, we are going to answer your questions. Okay, and also you can share this experience if you want with share buttons in on Facebook or YouTube. Okay, so we are going to start with this virtual experience, and the first thing I am going to do is to help you to understand the place of our visit. So we will begin with some information about the organization, the European Southern Observatory, or ESO. Well, in this case, ESO is composed by 16 member states, as you can see in this picture. The headquarters of ESO are located in Germany, and also Australia has also joined ESO as a strategic partner. In this case, Chile is the host state and is the home of all ESO observatories. Well, the headquarters, um, uh, uh, sorry, from the 1960s, and with those objectives in mind, well, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. Okay, so in this case, the mission of ESO is to design, build, and operate astronomical observatories. And why? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. Well, right now we are going to see a new picture here with the three observation sites of ESO in Chile. So, in first place, we have the Chajnantor Plateau, and this is the site of the ALMA and APEX radio telescopes. So, in this case, ESO is part of these places for radio astronomy, alongside other international partners. Additionally, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope. And this one is using the HARPS instrument. And HARPS is an exoplanet hunter. Well, and finally, we have the place of this visit, the Paranal Observatory. So this ESO observatory is the home of the Very Large Telescope, or VLT. This is the most advanced visible light telescope on the planet. In the next few years, we will also have the Extremely Large Telescope, or ELT, the biggest visible light telescope on Earth. Also, near there, the CTA will be an array of telescopes. In this case, they will be focused on capturing gamma rays. Okay, so now we have a better picture. So let's travel to the Paranal Observatory. We will take a look at this animation now. So now virtually you are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital, Santiago. Specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountaintop of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And where is the ocean? Well, the Pacific Ocean is located below of the cloud cover over there. And why those clouds? If right here the sky is so clear, dry, and lonely. Well, this is because of the influence of the Humboldt current. This is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy about the layer. Instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. So the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. So maybe can you see, can you imagine what other no, other natural barriers we have in this area? Well, about 200 kilometers to the east, we have the Andes Mountains with very high altitudes, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds coming from Argentina and Bolivia. The main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, we have here we are far away from artificial light sources because of the human activity. I mean, light pollution. So basically, this is one of the best places on Earth for astronomical observations. Okay, so right now we will change the view to have an even closer look to Paranal. So as you can see here, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. So do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. So this observatory is like a true oasis. You will see how in one of the driest deserts we have a lot of life, and of course we have a lot of science. Okay, so right now we will visit the summit of Paranal. Okay, so in front of us we have the Very Large Telescope, or VLT. its acronym. So if you see the amount of buildings, we have in this case 4 giant ones and other 4 small and rounded ones, such as this one. It is clear that the very large telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you can find the 4 unit telescopes, or UTs, each one with a primary mirror of 8.2 meters of diameter. So basically the giant ones in your screen. And the other small ones are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. So we have this is an auxiliary telescope, for example, but we have 4 of them. So this is one, this is the second one there, this is the third one, and this is the last one. Okay, so each UT has a name in Mapudungun language. This is the language of the Mapuche people from the south of Chile, from central and south of Chile, actually. So in first place we have Antu, and Antu means sun in Mapuche. The second one is Cuyen, and Cuyen means moon. Next one is Melipal. Melipal means 4 stars, but this is a reference to the Southern Cross constellation. And finally, we have Jepun. This is a concept associated with Venus. So it's basically something associated with the planet Venus. So as I told you already, the closer ones here are the auxiliary telescopes. The important thing about the auxiliary telescopes is that they are mobile telescopes. So we can move them using this rail here and this kind of stations in the ground. You see? So we have different stations and we can move the small ones up to 30 different positions. So basically they can be in different configurations, and they can be in a more compact configuration or more extended configuration, such as this one, for example. Okay, so they were specifically designed to work all together as a single big telescope with variable diameter. So it's able to reach up to 200 meters of combined power, as you will see in a few moments in a short video. Okay, so this technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. So right now, we will come back to the tour screen. Okay, so now you will have the chance to visit a telescope. So we are going to visit the UT3 Melipal. We can't enter all the telescopes, but don't worry about that, because the 4 ones are identical in size and shape. But the only difference are the instruments inside. You can learn more about the instruments on the ESO website. Okay, so now we are going to enter to this telescope. We are going to visit Melipal. And here we are. So what can you see? Well, this is a giant telescope. You see, we are on the last floor of this facility at the same height of the main mirror in front of us there. So the mirror, I will do a close up here. This mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thick, created from a ceramic and flexible material called cerudur. And the surface of this mirror, the reflective surface, is a very thin layer of aluminium. So this is basically the reflective material of this mirror. Now, how can we point this telescope to the sky without breaking it? Well, we are going to change the perspective, we are going to change the view, and I will show you now this telescope, but from the lower floor here. So I will change the perspective and I will explain something interesting about the mirror. Okay, so now we are in the lower floor and I will show you from here the mirror again. So in this case, the mirror is there, you see, and you can see that the mirror is basically mounted over this white structure. And this is a cell supporting all systems assisting the mirror, including something called active optics. And here you can see some little gray boxes. I am going to do a close up again so you can see the gray boxes. I am talking about this. Okay, so they are called actuators. They are kind of a piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror, because the mirror is concave. Otherwise, it could suffer deformations just because of gravity physics. So those deformations, even if they are imperceptible in a first view, could be critical in the result of the observations. Okay, so how can we observe with this big telescope? We are going to come back to the last floor to explain that. Okay, so from this location, we are going to share with you a short animation in order to explain how this telescope can receive light. So we have the simulation here, and the first step is, of course, that we have to open the dome. Of course, this is an exaggerated view, but we have to open the dome. And the first step is to receive the light using the primary mirror. And because the primary mirror is concave, the light will be reflected to a secondary mirror and then reflected again to a tertiary mirror. From there, it will be reflected up to three possible instruments. Those uh, that look like squares, red, blue, and green. So these are the instruments. So after that, when the instruments are receiving light, the light will be converted into a digital signal. And this digital signal will be transferred by fiber optics to the control room. So the astronomers are working from there. So in this case, and based on the animation you saw before, this, for example, is one of the instruments. You see, it's a big machine, and this is one of the instruments in charge of converting the physical light into a digital signal. So one more time, we have the primary mirror here, we have the secondary mirror here, and the tertiary mirror is not visible, but is located just in the middle. Okay, so there is another mirror here. So finally, the light is going to be received by the instrument. And you can see some people here. They are engineers. They are working every day to to fix some problem, to do maintenance, and basically to prepare the telescope for the next observation night. So basically, this is what happens in this telescope. And as you can see in this place, you have people working 24 hours. During the day, you have the engineers working, you have the people doing some calibrations, and during the night, you have the observers. I mean, the astronomers, telescope operators. Okay, but I am going to explain that in a few moments. Okay, so in this way, we are finishing this visit to the telescope, and now I will come back to the main platform again. Okay, so from here, the next stop will be the control building. This building, as you can see, is located in a different level. So this building is a very big building actually. This is from another perspective. But before visiting this place, I am going to stop for a moment to check if we have any question from the public. So, Hector, do we have some question from our virtual visitors?
We have several greetings. We have a greeting from Vasily, from Jane. She was looking forward to the tour. From All Music Video. From Jose Maria, one of our regular viewers. We have from Juan. From M23. From Observer Zero. But so far, none of them has posed any questions. So let me ask you a couple of questions myself. So the typical question that we receive in the tours is, what kind of maintenance or cleaning is needed to do to the mirrors in order to have good observations?
Yeah, sure. Of course, we have to do some maintenance on the mirrors because the mirror is the most delicate part of the telescopes. So in this case, I am going to enter again to the telescope, and I can tell you that the mirrors here they need well, basically they can they can have two possible maintenance, one easy maintenance and a more complex maintenance. The easy maintenance is done every month, and for this easy maintenance you need usually a couple of engineers, and they are going to rotate the telescope a little bit. So the engineers will they will spread a carbon dioxide snow on the mirror. So this is something like a foam, and this chemical will remove dust from the mirror because well, we are in the desert and we have dust in the environment. So basically the carbon dioxide will remove dust, so the mirror will look more or less clean. Okay. um, but we have a second maintenance, and this is more complex, and we need to do this maintenance every 2 years more or less. So for this complex maintenance, we need to remove all the mirror, including the cell, the white cell, from this building. We need to remove all of this. So when the mirror is outside, and I think you will see here that there is a yellow structure. So the mirror will be placed here, and those bars will drop the mirror very slow, very slow, very slow. So in order to uh, basically place the mirror on a special vehicle, and this vehicle is going to transfer the mirror down to the base camp. In the base camp, we have a special facility. It's called the mirror maintenance building. So you need to move the mirror there, and the mirror will be there for a process that is called recoating. Because I was explaining before that the surface of the mirror is made of aluminum. It's a very thin layer. So you need to remove this layer with some chemicals, and after that you need to put a new layer of aluminum. So after this process is complete, after more 2, 3, or 4 days, the mirror will look like a new mirror because you are actually changing the reflective surface. So after all of this is finished, you need to put the mirror again in the vehicle, the vehicle is coming again to the platform, you need to use this yellow structure again to lift the mirror, and then you need to move the mirror inside of the telescope, and the telescope will have the mirror again in the original position, so you can restart operations. So that's the maintenance process.
Okay, thank you for it. Another question, is it possible for viewers to visit the observatory in person?
Oh yeah, of course. We have a program of public visits to Paranal Observatory. We have visits every Saturday in two different tours at 10 a.m. and 2 p.m. So in order to visit Paranal, you need to do an online booking. You can use the ESO website to find the visits section, and basically you need to fill out your information at least 2 weeks in advance, maybe, because we have limited slots, 80 people per tour. So after that, you can visit Paranal, and you need to take in mind that the closest city is Antofagasta, and it's located 1 hour and a half away. So maybe you need to start your trip maybe 2 hours in advance, and you need to arrive to the observatory, and the tour guides will do the visit and will show you the facilities.
Thank you. We don't have any more questions, and I would like to encourage our audience to send us any doubt, any comments that they may have.
Okay, so thank you very much, Hector. So we are going to continue now. So as I told you before, the next stop is the control building, and the control building is located here. So I am going to show you this very interesting place, because this is the place where the scientists are located at night. Okay, so we are going to visit the control room, and here we are. So this place is basically uh, it's something like an office, as you can see. We have several separated workstations. So for example, we have workstations for each telescope. And in this case, for this workstation in particular, this workstation is only for one specific telescope, in this case for Melipal. This is the telescope we were before. So this workstation is only for the remote control of Melipal, you see. And at the opposite workstation, this one, this is specifically for UT4, see, for Japan. So only operations with Japan are from here. So you again, you have different computers for different purposes, and you have some people working here. Okay, so um, and if we continue working using this virtual corridor, we are going to find the additional workstations. This one, for example, is the station for UT1 and 2. So only operations with and 2 are from here. And the last station in the opposite side is for Guyen, for UT2. So basically, all the telescopes, instruments, and systems explained before are controlled from here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. We are going to enter to this specific workstation to explain something here. So each night we have a telescope operator and an astronomer per telescope. So for example, in this particular picture, this person is the telescope operator. Okay, so this person is in charge of the movement of the telescope, okay, to change the position of the telescope to observe a different object. And you also have an astronomer usually. So for example, let's suppose this is the astronomer. So The telescope operator, as I told you already, is in charge of the technical details and the movement of the telescope. So it's basically as the pilot of the machine. And the ESO astronomer, instead, is in charge to direct the scientific observations, and this person will decide the next steps. So it's more like the co-pilot. Now, the observations are performed by experts from ESO for scientists from all the planet. Okay, so this is basically what happens here. As you can see, it's an office space. So basically the people are working all night from here. Okay, so that's it regarding the control building. I am going to come back to the main platform again. And now you have a lot more information about the observatory and the people working here. So now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor. So scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, and also others located in the more distant places in our universe. So that's it. And now we are going to explore a list of the top 10 discoveries from the ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10, but we have something else. We have one more thing. So please, Hector, if you can put this additional video. This is additional news regarding that a team of astronomers were able to capture the first image of a black hole. So the Event Horizon Telescope, or EHT, its acronym, is an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration. And they were able to achieve the first direct evidence of a supermassive black hole. So the picture will reveal the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. This object is located 55 million of light years from Earth, and its mass is about 6,500 million times the mass of our Sun. So this is the picture. Okay, so we hope you like the top 10. This was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific staff behind them. So now we can continue, and from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. The moon is below the horizon, and the sky is full of stars. So here we can see as our first interesting portion of the sky, this is a very popular constellation, and it's just above the AN2 telescope. Okay, so this is the Orion's constellation, and I am going to show you this constellation here, so you can see it. So in the mythology, Orion represents a hunter, and you can recognize this constellation because of those 3 stars somewhat aligned. They are representing Orion's belt. And inside of Orion, we can see another interesting object. This is the Great Orion's Nebula. So this is very, very interesting because you can observe this nebula even with your naked eye because it's very, very bright. So of course, it's very, very impressive with binoculars or with a small telescope. Okay, so we are going to move from Orion, and we are going to change the position now, and we are going to move to the brightest star of the night sky. So we are going to move here. This um, this star here is the brightest star in the sky, and it's called Sirius. So this star belongs to the Canis Major constellation, representing one of Orion's hunting dogs. So, basically, the constellation of this star is called Canis Major, and it represents a dog in the mythology. This is one of the hunting dogs of Orion. So basically, the constellation related to the brightest star in the sky is connected in the mythology to this one. Okay, so now coming back to ANTU, the telescope here, I am going to show you something that is very close to ANTU. Is this object. This object here, just next to the telescope, we can see the Pleiades. The Pleiades is an open star cluster located in the Taurus constellation. Now, the majority of those stars are visually close to a very specific area, very populated with stars. So actually, when you are looking at this area in the sky, you are looking at one of the Milky Way arms. So if you look carefully, for example, from this perspective, you can see that all this area has much more concentration of stars. Okay, this is because this is one of the arms of our galaxy, the Milky Way, and our sun is only one among hundreds of millions of stars. Okay, so during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between Scorpius and Sagittarius. So, and this is interesting because you can see all this area from the southern hemisphere. Okay, so this is basically what happens here and what happens in this portion of the sky. But now we are going to move to another sector to find two spots in the night sky. So those ones. We are going to do a close-up, and basically those spots right here are the Magellanic Clouds. Up there is the large Magellanic Cloud, and down there is the small Magellanic Cloud. They are not actually clouds, of course. They are galaxies with an irregular shape. Both of them are visible to the naked eye in a clear night like this one. This name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were unaware about what a galaxy is. So something else we have near here, another important area, is the smallest constellation of the sky. The smallest constellation in the sky is called the Southern Cross, and I will show you the Southern Cross right here. In this picture, the Southern Cross looks a little bit tilted. But this is an easy constellation to find in the sky, and it's only visible in this hemisphere, and it's a very good guide to find the South Celestial Pole. The South Celestial Pole is basically a projection of the Earth's South Pole. So during the night, the stars appear to revolve around this point. So to find this point, we have to do something with the help of the Southern Cross, because in the Southern Hemisphere, we don't have any bright star next to the the South Celestial Pole. So the solution is to project the longer stick of the Southern Cross about 4.5 times. And I will do that. I will project this stick like 1, 2, 3, 4.5, and more or less like here, we have the south celestial pole. So basically, if you take an astrophotography toward this direction, you will see a lot of concentric circles, like the star trails, and this is because this is the projection of the south pole of our planet. And finally, if you look at the horizon in the same direction of the south celestial pole, basically you are looking at the south cardinal point. Okay, so this is why it's interesting to know where is located the south celestial pole. Okay, so this is the conclusion of our visit to Cerro Paranal. This is the conclusion of this visit to the night sky. So we are going to return to the platform in the daytime now in order to visit the last stop of this virtual experience. So to visit the last stop, we are going down from the mountaintop. So we have to go down to the 2,400 meters above sea level in order to visit a very special facility. For this purpose, we have to go into this direction. We have to visit the base camp of Paranal. This is the base camp. As you can see, this is like a mini city because we have different offices, rooms for contractors, mirror maintenance building, the warehouse, etc. So we have a lot of different facilities here. And the place I am going to show you is this one. It's called the residence. The residence of Paranal is the place where the ESO staff can stay and rest. So in order to enter and to access to this place, I have to use this ramp, and I will show you what happens in the inside. So this is not an underground facility. It looks like, but it's not an underground facility. This is the roof of the residence, but in the opposite side of this residence, you have a normal, regular wall with windows. Okay, so it's just this area that you need to access using this ramp. Okay, so I am going to enter now. So the residence is the home of the ESO staff during its work in the desert. So here the workers can enjoy a more humid air. They have a swimming pool, green areas, and also, of course, it's a much more comfortable location if you compare to the desert and the intense sunlight from the outside. So from this perspective, for example, we can see this is the restaurant, this is the lobby, this is the reception. So it looks like a regular hotel that is only for the staff. So we cannot allow tourists coming here. Okay, so with this nice view of the Paranal residence, I think this is the time to look if we have additional and last questions from our visitors.
Okay, so we have a couple more greetings from Sway Graven, another of our regular viewers, and also from Viton VC. We have a question here from Jane. How many people work at Paranal Observatory?
Well, we have a mix between ESO staff and contractors. It's not always a fixed amount of people, but it's about 200 people, because you need astronomers, of course, you need engineers, you need people doing maintenance, you need people in the kitchen. So it's more or less about 200 at any single day in Paranal, in between 200 and 250, something like that.
Okay, I have here a comment from Jessica saying that she's not understanding our English. Pero, Jessica, aprovecho de mencionarte que estamos haciendo estos tours también en español. Vamos alternando entre español e inglés, Observatorio Paranal, Observatorio La Silla. Así que si te puedes unir para cuando toque en español, ahí puedes entender todo lo que estuvimos diciendo. So for everybody, just going to repeat myself. We are making these tours both in Spanish and English. We're alternating. And we're also alternating between Paranal Observatory and La Silla Observatory. So keep an eye from when the next tour is. And we have a question here from Jose Maria. So one question of a bit off topic, he mentioned. Is it true that in the movie Interstellar, the size of the black hole seen from one of the exoplanets should be more bigger than it was shown? I have no idea about the size, but I do know that the black hole, as it was shown in that movie, was very accurate. It was a result of several very well done simulations, and there was physicists involved in that. If I recall correctly, it was Sean Carroll, the physicist who was involved with that particular movie. And he's a very known physicist. And the simulation of the black hole was one of the most realistic ones that we have ever made, as far as I know. But regarding the size, I have no idea. I mean, it's a movie. Clearly, some things were also exaggerated for science, but not for science, for Hollywood purposes, let's say. And with that, I don't see any more questions. So just going to say my goodbyes. It was my pleasure to be here with you today. And please share this experience with everybody you know that might like it. As I already mentioned, we are going to keep doing this every Saturday. Paranal Observatory, the Sea Observatory, but also Spanish and also English. So keep an eye for what the next tour is going to be.
Okay, thank you very much, Hector. And yeah, so we remind you that all these visits, information, and pictures are available from the ESO website. And we also have a survey, so you can send your questions, I mean, your feedback about this virtual experience using a survey. And the link is, I think, in the chat window now. So yeah, from my side now, I hope you like this virtual experience. Please stay updated with ESO social networks in order to know when we will have the next tour in Spanish or English, La Silla or Paranal. Okay. So on behalf of ESO, I want to say thank you very much for your presence and goodbye.
Goodbye.